then it is an exponential family. If I am considering, say, x following Poisson distribution with parameter lambda, then this is an exponential family. I also we can consider, say, for example, geometric distribution. Okay, geometric distribution. Yesterday I discussed one form. Let us write that form or another form. Anything we can write. So in the exponential family, if we want to write this, we write like this. So it is 1 minus p to the power, say, k minus 1 into p. Well, k I will write as x here because in the form I have used x there. So this is for x equal to 1, 2, and so on. Yesterday I had written the form 1 minus p to the power x into p for x equal to 0, 1, 2, and so on. So both are same. We can write for any of them. Alternatively, we can write like 1 minus p to the power x into p, x equal to 0, 1, 2, and so on. So both are okay. Now this one, suppose I take, okay, this you can write as p into e to the power x log 1 minus p. So here this can be considered as your Cp, and Hx is actually equal to 1 because there is multiple is 1 here, and this is your Tx, and this is your Q of P. So geometric distribution also belongs to the exponential family. If you take this particular form, then it will be a little bit modified. You can write it as P by 1 minus P, and then you write e to the power x log 1 minus P. Then also it can be considered as the distribution in the exponential family. So geometric distribution belongs to exponential family. Let us take, say, negative binomial distribution. Okay, say R and P, where R is known. If R is unknown, then this will not be in exponential family, as you will see. Suppose I write this form of the distribution here. It is x plus r minus 1 c r minus 1 1 minus p to the power r 1 minus p to the power p to the power r, and this is x. So these many failures, and then you can have this. So x is equal to r and so on, r plus 1. So this we can write as x plus r minus 1 c r minus 1 p to the power r e to the power x log 1 minus p. So again you can see that this can be considered as hx. This is c of p, this is t of x, and this is q of p. So negative binomial distribution with r is known, then it can be put in the form of exponential family. But if r is unknown, then I cannot put this here, because here x plus r minus 1 c r minus 1, this involves both x and r. So this cannot be separated out. So when r is unknown, negative binomial is not in exponential family. We have discussed two forms of the normal distribution with one parameter. Let us write that. So normal mu1, if I consider, then what is the form of the distribution? It is 1 by root 2 pi e to the power minus 1 by 2 x minus mu square. This we write as 1 by root 2 pi, and this exponent we simplify. We can write it as x square by 2 minus mu square by 2 plus mu x. Okay. So then this we write as 1 by root 2 pi e to the power minus x square by 2 e to the power minus mu square by 2 e to the power mu x. Then this term we can consider as hx, this as c mu, this is q mu, and this is tx. Okay. So normal distribution with one parameter is again in exponential family. Here I have taken mu to be the parameter. Let us take the second one. Suppose I consider normal 0 sigma square. Okay, so here sigma square is the parameter. And let us consider the form here. So it is 1 by sigma root 2 pi e to the power minus x square by 2 sigma square. Then you can consider, say, this as c sigma square, this as hx, this as tx, and minus 1 by 2 sigma square as q sigma square. So this is again in the exponential family. So are these examples clear? Are you able to follow these examples?
Yes, sir. Yes, sir.
Now, if I consider two parameter normal distribution, then I need to define multi-parameter exponential family. So let me consider that also here. So we will say that the distribution is k parameter exponential family if it is of the form fx theta is equal to, okay, so I'll write two equivalent forms, hx e to the power sigma qi theta tix I is equal to 1 to say k. So in place of one term here, now I have q1 t1 plus q2 t2 plus qk tk. Another equivalent form is we write it as c theta hx e to the power sigma theta I tix. Okay. See here I have written qi theta, but suppose I call these qi thetas themselves as thetas. Okay. Then this is called k parameter exponential family. So let us consider say normal distribution with two parameters mu and sigma square, and let us see that we can actually put it in that particular form. 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square x minus mu square. So this is equal to 1 by sigma root 2 pi, and this part I will split like this, x square by 2 sigma square e to the power minus mu square by 2 sigma square and e to the power mu x by sigma square. So this we write as, see, this particular term is a function of the parameters. Okay. So this we can write as c theta, and then you have this 1 by root 2 pi, we can consider it as hx, then e to the power theta 1 x plus theta 2 x square. So this theta 1 I am taking to be mu by sigma square, and theta 2 I am taking to be minus 1 by 2 sigma square. So this is a 2-parameter exponential family. Let me start with the 1-parameter exponential family and see that what happens to this concept of Rao-Kramer lower bounds. Okay. What happens about the Rao-Kramer lower bounds here? So let me write the standard form in which I have written the form of the 1-parameter exponential distribution. That is c theta hx e to the power q theta dx. So in order to obtain the lower bound, you have to consider log of fx theta. So that becomes log of c theta plus log of hx plus q theta dx. Okay. So if I consider derivative of this with respect to theta, I will get 1 by c theta into c prime theta. Derivative of log hx will become 0, and then you will have tx into q prime theta, where prime simply means the first order derivative. So what is sx theta? If you remember, it is nothing but the sum of this I is equal to 1 to n del log fxi theta by del theta. So that becomes, let me write it in the next line. So this is equal to n times c prime theta by c theta plus q prime theta sigma ti x, where x I am using x1, x2, xn, because I am writing for n of them if the sample size is n. This calculation is clear. Is this calculation clear to you?
Yes, sir.
Now you see this sx theta, it's a linear function of sigma tix. So either I consider sigma tix, I consider 1 by n sigma tix. So what happens? Which functions will have their RCLB attained? That means linear functions of mean of ti's, if I call it t bar, let us call, let us define, say t bar is equal to 1 by n sigma tix. Then t bar and sx theta are linearly related with probability 1. So if I call, say W is UMV UE of its expectation. It will be the minimum variance unbiased estimator of its expectation. Another thing is that as it will attain RCLB. Now the question is that what is the, I mean, like, what would be the expectation? So let us also look at this part. So I'll just use the form of the distribution. Okay, what is expectation T or expectation of W, etc. So let me consider the distribution. See, distribution. Once again, see, I am writing here integrals, but yesterday I have explained that if the summations are there in the discrete case, then the calculations will be similar. It is more elegant mathematically to write the integrals. So without any failure, I am just writing like this. Okay. Replace integral by summation. Okay. So now you write the form here, because this is c theta hx e to the power q theta tx. Okay. And this you differentiate with respect to theta. So that assumption we are making here, that the differentiation under the integral sign is allowed. And for the distribution in the exponential family, actually it is true. So what we will get, here first term, if I differentiate, I will get c prime theta. So it is e to the power q theta tx dx, plus in the second part, it is e to the power q theta tx, and you will get q prime theta tx, derivative of this, that is equal to 0. So the first term, see, if I divide by c theta and multiply by c theta, then it will become integral of the density function. So this term will become 1. And what is the second term? Second term is nothing but q prime theta expectation of tx, because it is this thing multiplied by the density function integral. So that is nothing but this. So what you have got, this means that expectation of tx is nothing but minus c prime theta by c theta q prime theta. So even the form that what we have got, so expectation of t bar, that will be equal to this. So t bar, let me call it, say, eta. This is umv of eta. Binomial, Poisson, geometric, okay, negative binomial, exponential, normal, normal 0 sigma square, gamma r lambda, and So I'm giving you a detailed exercise here, which you should do. Out of this, I will do only one exercise. See, binomial, Poisson and all we have already done. Let me take one exercise here out of this. So let me take, say, geometric here. Okay. So in place of P, I'll put theta here. And I'll consider the form which I considered yesterday in the class. That is theta into 1 minus theta to the power x for x equal to 0, 1, 2 and so on. Okay. So here, of course, theta lies between 0 and 1. And we are able to write it in the form of exponential family. How? Just like this. Theta into e to the power x log 1 minus theta. So what is your c theta? C theta is theta, hx is 1, and q theta is log of 1 minus theta, and tx is 1. Okay, tx is x. So what is this term? That is eta, that is minus c prime theta by c theta q prime theta. So that will become c prime theta is 1, c theta is theta, and this will become 1 by 1 minus theta with a minus sign. So that will become theta minus 1. 1 by 1 minus theta. Yeah. So with a minus sign when we put, and then there is a minus here. So it will again become 1 minus theta. So it is actually 1 by theta by theta. That is 1 by theta minus 1. So Tx is x. So this means that x bar is UMVUE of 1 by theta minus 1. Or we can also say x bar plus 1, because linear function we can always take. So this is the result that we get here. X bar minus 1 is UMVUE for 1 by theta. Okay, so is this application okay to all of you?
Yes, sir.
So remaining problems I am leaving as an exercise to all of you. Like you apply this result to these well-known distributions. There are many more, of course. You can consider one parameter exponential distribution. You can consider say beta distribution and so on. So there are so many distributions where these results can be applied, even Weibull distribution, etc. But of course, there we have multi-parameter situation. So you take one parameter at a time, because for all parameters you cannot apply this result. I have already discussed the concept of efficiency of an estimator. When do we say one estimator is more efficient than the other estimator? So any of you remember the definition? When do I say? Yeah, please say it again.
Mean square error is there.
Mean squared error. So actually mean squared error concept came little later. Initially the concept was for the unbiased estimators only. So it was for the variance. So for the sake of completeness, let me define these things also, because later on when you are reading from the books, you will come across different terminologies. So you should be familiar with all of them. I mean, mean squared error, I have already defined. That is the most, you can say, frequent version. That is the based on the decision theoretic concept, that the mean squared error of one estimator is less than or equal to the mean squared error of another estimator. Then the first estimator is said to be better than the second estimator, or it is also called more efficient. However, if we are restricting attention to unbiased estimators only, then variances have to be considered. So relative efficiency, etc., has been defined classically from 1920s onwards. So for the sake of completeness, let me define these things also. So let us consider, say, let T1 and T2 the relative efficiency of T2 with respect to T1. This is defined as variance of T2 divided by variance of T1. Okay. So if I get this value as less than 1, it means T2 is more efficient than T1. Okay. Otherwise, we will say T1 is more efficient than T2. So if efficiency of T2 given T1 is less than 1 for all theta, we say that T2 is more efficient than T1. Another extended concept is that of with respect to Rao-Kramer lower bound. So let me write that also. Since we have shown that RCLB is the smallest value that the variance of an estimator can achieve, therefore we can compare with that. So it is written like this: efficiency of an estimator T, that is defined as variance of T divided by RCLB. So in general, this efficiency will be greater than or equal to 1. In general, efficiency of T will be greater than or equal to 1 for all theta if it is equal. If equality is attained for all theta, then T is UMVUE. Okay. What happens that many times we will not be able to actually attain this thing, but in the limit it can be achieved. So sometimes we have that limit of this efficiency of T as n tends to infinity is 1. Then we say that T is asymptotically most efficient. So these are all related concepts. Earlier I have mentioned, for example, method of moments estimator, maximum likelihood estimator, etc. I gave few properties of the maximum likelihood estimator. However, I will like to give more properties in the context of this new concept of asymptotic efficiency. I will in fact show that the maximum likelihood estimator is asymptotically most efficient. Anyway, to talk about that little later, firstly, let me continue this discussion of the efficiency. So let me take one example of efficiency with respect to the RCLB. Okay. So let us take again a known problem, like for example, Poisson distribution we have already discussed. However, I am not interested to estimate lambda, but I am interested to estimate something else. Okay. We are interested to estimate probability x is equal to 0. So this is my G lambda. Okay, so why this is important? Of course, you can simply say that for lambda, I have got an estimator x bar. So I can put e to the power minus x bar, isn't it? But unfortunately, it is not a linear function of x bar. Therefore, this will not be unbiased. Suppose I am looking at the unbiased estimation, then what should we do? So let me look at this. So first of all, what is the lower bound? If you remember, the lower bound for the variance of an unbiased estimator for lambda, based on the sample x1, x2, xn, it was lambda by n. Here I have taken only one observation, x, so it will be simply lambda. Okay. So RCLB for lambda for variance of an unbiased estimator for lambda is lambda. Okay. So if you apply the formula for function, it will become G prime lambda upon that. So what is G prime? G prime is e to the power minus lambda. G lambda is e to the power minus lambda. So G prime lambda is minus e to the power minus lambda. So G prime lambda square will become simply e to the power minus 2 lambda. So RCLB for variance of an unbiased estimator of G lambda, that is e to the power minus lambda. So it is lambda e to the power minus 2 lambda. I will consider some unbiased estimator here. Let me call it, say, beta x. So that I am calling to be 1 if x is equal to 0, and it is 0 if x is 1, 2, and so on. Okay. This estimator yesterday I have shown you in the context of geometric distribution. So same thing here, 1 into probability x equal to 0 plus 0 into probability x is equal to not equal to 0, I can simply write. So this is simply e to the power minus lambda. So this is unbiased. So beta x is unbiased. However, what happens to its variance? Let us see that. So expectation of beta square x, that is also the same, because in place of this I will get 1 square probability x equal to 0 plus 0 square this one, which is again e to the power minus lambda. So variance of beta x, that is equal to e to the power minus lambda minus e to the power minus 2 lambda, which I can write as, okay, which is obviously greater than lambda e to the power minus lambda, because this is greater than lambda. You know this expansion. So in your maths 1, etc., you have done some such exercises. 1 minus e to the power minus x is greater than x for x positive. So this is greater than this. So it means, sorry, this is e to the power minus 2 lambda, not this one. Basically, this is equivalent to e to the power, I can just write like this, e to the power lambda greater than 1 plus lambda. This, you know, it is always true for lambda positive. Okay, for lambda positive, this is always true. So estimator beta does not achieve RCLB. So actually efficiency of beta, that is variance of this, that is e to the power minus lambda into 1 minus e to the power minus lambda divided by lambda e to the power minus 2 lambda, which is actually equal to 1 minus e to the power minus lambda divided by e to the power minus lambda lambda, and I can write it as e to the power lambda minus 1 by lambda, which is always greater than 1. Okay. So if I am considering this an unbiased estimator, I am unable to prove that it is minimum variance unbiased estimator, although it looks to be very reasonable estimator here. Again, in the geometric distribution, if you remember, I had shown directly that actually it is the only unbiased estimator. Let us try whether similar thing can be shown here also. Let us find an unbiased estimator by solving the equation, say expectation of gamma x is equal to e to the power minus lambda. Okay, where gamma I am taking to be unbiased estimator. So what this will give me, gamma x e to the power minus lambda lambda to the power x by x factorial, that is equal to e to the power minus lambda for all lambda positive. I can remove e to the power minus lambda from both the sides and consider the expansion. So this will give me gamma 0 plus gamma 1 into lambda plus gamma 2 lambda square by 2 factorial and so on. This is equal to 1 for all lambda positive. On the left hand side you have a power series in lambda, on the right hand side you have a constant. So the two can match on an interval because lambda is positive, that means it is on the true for all positive real numbers. It is possible only if and only if all the coefficients match. Will match if and only if all coefficients match. So I will get gamma 0 is equal to 1, gamma 1 is 0, gamma 2 is 0, and so on. This means beta x is equal to gamma x for all x. So basically it means that beta x is the only unbiased estimator. So beta x is UMVU. So in this case, actually unique unbiased estimator comes and therefore the problem becomes very, very simple. Is this example clear?
Yes, sir.
Let me give one more example of efficiency here. So let me consider some arbitrary distribution. Let x1, x2, xn be a random sample. From a distribution with mean, say mu, and variance sigma square. Let us consider two estimators. Say T1 and T2 for estimating mu as, so T1 I take to be simply the mean of all the observations, but in T2 I will get little bit modified. I will put it as 2 by n into n plus 1 sigma I xi, I is equal to 1 to n. Okay, so a little bit modification I have done in the second one. Okay. We have already seen that T1 is unbiased and consistent for theta, for mu. Okay. So let us take T2 and see what happens. If I consider expectation of T2, then it is 2 by n into n plus 1. Sigma I is equal to 1 to n I expectation of xi, which is mu. So mu, then 2 by n into n plus 1 sigma I. Sigma I is n into n plus 1 by 2, so this whole thing cancels out, so you get only mu. So T2 is also unbiased. What about it, variance of this? So if I consider variance of T2, then it is 4 by n square n plus 1 square sigma I square variance of xi. Variance of xi is sigma square. So this becomes 4 sigma square by n square into n plus 1 square. Sigma I square, I is equal to 1 to n. This sum of this one you already know. Okay. So this is equal to 4 sigma square by n square into n plus 1 square. This is n into n plus 1 into 2n plus 1 by 6. So anyway, you can just simplify this. This is small. So 2 by 3, 2n plus 1 by n into n plus 1, because n into n plus 1 will get cancelled out. 4 by 6 is 2 by 3, then sigma square. Again, you can see that this term actually goes to 0 as n tends to infinity. So T2 is unbiased and its variance goes to 0. So we have done the theorem that T2 is also consistent. So both T1 and T2 are actually good estimators. However, let us compare the efficiency here. So what is variance of T2 divided by variance of T1? So that is 2 by 3. That is sigma square by n. So this is 2 by 3, then 2n plus 1, and n will cancel out, you will get n plus 1 only. Because here you have n into n plus 1, and for T1 you have variance of T1, you know, it is sigma square by n. So this term, if you see, this is actually greater than 1. So T1 is more efficient than T2. That is, the simple arithmetic mean is better than this weighted arithmetic mean here. So I hope this is clear, this discussion. I will explain this concept of relative efficiency with another example. Okay. Is this example clear to all of you? Are you able to hear me?
Yes, sir.
So let me take another example. Let x1, x2, xn follow normal 0 sigma square. We have already seen that for sigma square, we can consider estimator like 1 by n sigma xi minus x bar square, 1 by n minus 1 sigma xi minus x bar square, etc. We have also compared their mean squared errors. Okay. But here what I will do in place of sigma square, let us consider estimation of the standard deviation, that is sigma. Suppose we want to estimate standard deviation sigma. Okay. So 1 by n minus 1 sigma xi minus x bar whole square, expectation of that was sigma square. It does not mean that if I change that to s, that means if I take a square root, then it will be expectation, it will be equal to sigma. Because expectation is a linear function, it's not a non-linear function. Okay. So let us see term by term. I can consider square root of s square and look at what is the coefficient I will get. Another thing is I can also consider based on absolute values. Okay, so I can consider various things. First of all, let us look at the RCLB. Okay. So although we have calculated for sigma square, but that was for normal 0 sigma square. So here that is 2 sigma to the power 4. Okay. So if I am considering square root of that, so I will get square root sigma square. So derivative of that will be 1 by sigma square to the power half. Okay, 1 by 2 sigma square to the power half. So if I put square of that, I will get 1 by 4 sigma square. So I will get sigma to the power. So I can just write here sigma 2 sigma to the power by n 1 by 4 sigma square. So this will give me sigma square by 2n. Okay. How many of you understand this calculation here, which I have written just in a abbreviated form? Do you follow this calculation here?
Yes, sir.
Because I calculated for sigma square in the last class, that was 2 sigma to the power 4 by n. And if I am considering sigma as sigma square to the power half, so this is your g sigma. Okay, so g prime sigma will become 1 by 2 sigma square to the power half. So g prime sigma square will give me 1 by 4 sigma square. So that straight away gives me RCLB here. So I don't need to do this fresh calculation here. Let me leave that part. Our aim is to look at some of the unbiased estimators here. Okay. Okay. So yesterday you remember 1 by n sigma xi square was UMBUE for this problem. So if I take a square root of that, it will not be having expectation sigma. So can I adjust that? So let us look at it. Okay. So consider W is equal to sigma xi square by sigma square. That follows chi-square distribution on n degrees of freedom. Okay, let me look at the distribution of this 1 by 2 to the power n by 2 gamma n by 2 e to the power minus w by 2 w to the power n by 2 minus 1. So if I consider expectation of w to the power half, what I will get? So that is 1 by 2 to the power n by 2 gamma n by 2 e to the power minus w by 2 w to the power n plus 1 by 2 minus 1. So this is another gamma function. So this is equal to 2 to the power n plus 1 by 2 to the power n by 2 gamma n by 2 gamma n plus 1 by 2. So that is square root 2 gamma n plus 1 by 2 divided by gamma n by 2. And what is w? W is sigma xi square by sigma square. So what I get here, expectation of square root sigma xi square is equal to root 2 gamma n plus 1 by 2 by gamma n by 2, and this sigma I will bring to this side. So I adjust the coefficients here. That gives me gamma n by 2 by gamma n plus 1 by 2 root 2 square root of sigma xi square. If I call this estimator as say T1, then this is unbiased for sigma. Okay. I hope this calculation is clear to all of you. If I want to compare whether the how much efficient it is with respect to RCLB, then I need to look at the variance of this because this is unbiased. So let us look at the variance of this. Okay. So variance of T1, that is equal to 1 by 2, then gamma n by 2 divided by gamma n plus 1 by 2 whole square, variance of sigma xi square to the power half. So that is equal to 1 by 2 gamma n by 2 by gamma n plus 1 by 2 whole square, expectation of sigma xi square minus expectation of sigma xi square to the power half whole square. Both of these terms we have calculated just now, so I'll just substitute from there. So that is equal to the coefficient. See, this is n and then sigma square will come. So and then this one we have just now written, that is 2 times gamma n plus 1 by 2 divided by gamma n by 2 whole square, and then sigma square. So sigma square I will keep outside, and these terms will remain. That is half gamma n by 2 gamma n plus 1 by 2 whole square, and this is n minus 2 times gamma n plus 1 by 2 by gamma n by 2 whole square sigma square. So if I multiply by this inside, the term can take this particular form, that is equal to n by 2 gamma by n plus 1 by 2 square minus 1. And RCLB was sigma square by 2n. So how does it compare with this? So I will ask you one exercise here. You can use Stirling's approximation, and second is write a code, okay, to evaluate numerically. Although you don't have to actually write a code because this is readily available, this gamma function. So you can just put it there because you have to compare this term with 1 by 2n. Okay, so that is the comparison part. But I am leaving it here because I don't want to do this numerical part right now. I think you should do yourself. Of course, it is not very difficult. Let me construct another estimator. So take mod of xi. Okay. So if I consider expectation of mod of xi, what is the term I will get? So mod of x 1 by sigma root 2 pi e to the power minus x square by 2 sigma square. Okay. This is an even function, so you can immediately do all these things just using the simple properties of the gamma function. X so I'm just writing down the final expression here. That is not difficult for all of you. Okay, so this checking part you can do. So if I adjust the term to the left hand side, what I will get? I can write an estimator T2 as, so this I bring to the left hand side. So I can write something like 1 by n root pi by 2 sigma mod of xi I is equal to 1 to n. Okay. So this is unbiased per sigma. Again, you can look at the variance of this. Variance of T2 is equal to pi by 2n n times variance of mod of xi, which is nothing but pi by 2n. Pi by 2 n will get cancelled out. I'm sorry, this is square will come here. Yeah. So pi and then n will come here. So this is, yeah, pi by 2n and then expectation of xi square minus expectation of mod xi whole square. This term we calculated just now, so I will have to just substitute there. So this is equal to pi by 2n 1 minus 2 by pi sigma square, which we can write like this, pi minus 2 by 2n sigma square. Pi is 3.14 something, so this is greater than 1. So this is obviously greater than 2n. Okay. So I put this as an exercise. Okay, you can write it, program and do this thing. Are you able to hear me?
Yes, sir.
Yes, sir.
I'm not seeing any response actually. So I think in between I was muted for some time, and I don't know whether you saw that thing, or are you able to hear me before?
Yes, sir. Sir, sometimes we are not able to.
Yeah, but you should tell, na? If you don't tell, how I will know? After this concept of lower bounds was developed by Rao, Kramer, etc., then there were attempts to extend it to higher dimensions. That means either we have multi-parameter situation, or in the Rao-Kramer lower bound, one derivative has been used. Okay. So if we go for higher order derivatives, then what can be done? I mean, what will be the consequence of that? So based on that concept, some people started working on that. And first of those bounds is Bhattacharya's bound in 1946 he developed. So I will write down the statement. Actually, the regularity conditions will involve that you can differentiate more number of times in place of once, and other conditions will remain the same. So basically, the extension is simply of regularity conditions, but you get a stronger result. So let me just write it here. Let x1, x2, xn be a random sample from a population with probability density function or probability mass function fx theta. So parameter I am still taking to be one dimensional. I will look at the effect of the so theta belongs to, I have used actually script theta, so I will use the same notation. An interval on real line earlier I have defined sx theta, so I will consider now six theta. That is now ith order derivative of this product j is equal to 1 to n f of xj theta divided by earlier you remember it was del fx theta by del theta. So we had taken actually log there and summation was put there. Now since it is higher order derivative, so I am writing it in the product form. Okay. So del ith order derivative with respect to theta of the product divided by the product. Okay. And this I am defining for I is equal to 1 to k, etc. That means we can go to k equal to 2, we can take k equal to 3 and so on. Okay. We consider following regularity conditions. One, that is the ith derivative of the density must exist. Then only for the product it will exist. Once again, I am writing in the terms of integrals, but the same thing will be replaced by summations in the case of discrete. I mean, this will be like this if it is discrete. Okay. Earlier we have written it can be differentiated. Now I will say it can be differentiated I times. And these terms that we will get after differentiation, they s1 x theta and so on, sk x theta, they are linearly independent. Okay. For any estimator delta of g theta, this expectation of this, that is delta x, and then same thing, that is product fxj theta dx, j is equal to 1 to n, or summation, of course. So we define some more quantities now. Let us consider lambda I that is equal to variance of SI. I is equal to 1 to K. Let us also define lambda Ij, that is covariance between this Si and Sj. For Ij not equal to J. Both are of course from 1 to K. So we have the matrix lambda which has these terms lambda 1 1, lambda 1 2, lambda 1 K, lambda 2 2, so lambda 2 1 and so on, lambda 2 K, lambda K K. This is a K by K matrix, okay. We also define some term like eta I is equal to covariance between T and Si. And expectation of T is actually G theta. So T is an unbiased estimator, okay. T is unbiased estimator. So what will be the lower bound for the variance? So RCLB we have seen. Now we will see Bhattacharya bound, okay. So this actually you can simplify. This is I is equal to 1 to K. If I consider vector eta as eta 1, eta 2, eta K, this is transpose here, okay. Then that is greater than or equal to eta transpose lambda inverse eta. So this is a higher dimensional generalization of the Rao-Kramer lower bound. Here the higher order derivatives have been used. In place of first order, you can have higher order derivatives. So this, of course, if you want to expand it, it will be like double summation lambda Rs del R G by del theta R del S G by del theta S. For K equal to 1, this will be same as Rao-Kramer lower bound. Writing down of the expressions is complicated because several terms I have written here, but I hope all of the terms are clear to you. Is that okay to all of you? So let me write the proof of this. Expectation of Tx is equal to G theta. Like in the RCLB, what we had done, we had considered differentiation of this. So same thing we will do here also. So Tx, rather than writing multiple integrals, I will write only one integral. I think that is enough. Now what we will do, we will differentiate this, but earlier we have differentiated once. Now I can differentiate to 2 times or 3 times, in general I times. So let me write the statement like that. Differentiation 1 with respect to theta I times. Okay. So what I will get? This will give me Tx and derivative of this, that is nothing but Si. Because I will get del I by del theta I, product of f xj theta. Okay, j is equal to 1 to n. So I can consider divisor also product of fxj theta, j is equal to 1 to n, and here product of fxj theta, j is equal to 1 to n dx. That is equal to del di g by d theta I. So the left hand side, this term is nothing but Si x theta. So this is nothing but giving you expectation of T into Si, that is equal to, basically this term is nothing but eta I. That is what I have written there. Earlier we have seen expectation of S1 etc. was 0, expectation of Sx theta was 0. So same thing will be true here also, expectation of S1, S2 etc. will be 0. So this is nothing but covariance term. For all I, this is going to be 0. So now what we consider, earlier we have used the correlation inequality or the covariance inequality. Now since I don't have one term, I have several terms. So I will consider multiple correlation coefficient between T and S1, S2, Sk. I call it R square, that is eta prime lambda inverse eta divided by variance of T. And of course, as the correlation coefficient, same thing with multiple correlation coefficient also, it is less than or equal to 1. So this means that variance of T is greater than or equal to eta transpose lambda inverse eta. So this proves the Bhattacharya lower bound. This formula for the coefficient of correlation, you can just see any book on multivariate. Okay. Or maybe I can give the expression in the next class. I will just give you some sort of interpretation for this multiple correlation coefficient. Although you will be doing it in some other courses also, like regression analysis. But maybe I can just give it in the next class about an explanation about how to obtain this. Okay, so is this derivation clear? Is the derivation clear? Is the derivation clear?
So can you explain it again?
So the regularity conditions were modified from the Rao-Kramer lower bound to higher order derivatives. Earlier we have written that they can be differentiated. Now I have written differentiated I times. The starting point for RCLB was expectation of T is equal to G theta, and this expression we differentiated with respect to theta. Now I will differentiate I times. So if I differentiate it I times, this is the derivative, and then I am putting this in the denominator and I'm multiplying here so that this becomes expectation. This term is nothing but SIX theta, and this is TX. So this is nothing but expectation of T into SI. And the right hand side is of course eta I that I have already written there. So since expectation of SI, earlier you have seen in the RCLB that expectation of S was 0. So expectation of S1 is 0, expectation of S2 is 0 because they are only higher order derivatives. So the right hand side will remain 0. So expectation of TSI is nothing but the covariance of TSI, that is equal to eta I. Now at this point in the RCLB, I had applied the correlation inequality, that is rho is less than or equal to 1. That is rho square less than or equal to 1. But here what we will do, we will, because there is not one term, there are several terms. Because if you take each of them, you will get one inequality. Okay, that is, for example, I can put variance of T greater than or equal to this divided by variance of SI, or that is, so that is expectation of S1 square, S2 square, and so on. But that is the same as RCLB, because except that the order of derivatives will change. But to get a more sharper inequality, we consider all of them together. And if we consider all of them together, then I get a term like eta prime lambda inverse eta by variance of T. So this is less than or equal to 1. That gives me easily, because this term I am adjusting here on the left and on the right hand side. So this one will give me that variance of T is greater than or equal to eta transpose lambda inverse eta. Now, of course, since we have used all of them, there must be some advantage. Otherwise, why should we consider this more complicated situation? There must be some advantage of this inequality, this Bhattacharya's bound. So I'll just list all of them one by one. Is the argument clear to you?
Yes, sir.
So earlier we have written covariance term or the correlation term between T and S. Now in place of that, I am writing multiple correlation coefficient between T and S1, S2, Sk. So that single correlation coefficient has been replaced by multiple correlation coefficient, and this relation is used here. What we have written here, that covariance of T by Si is equal to eta I. So if you divide by variance, square root of variance of T, or you can put a square here. So here I will get a square term here, and then you put them in the matrix form, and then you take it to the one side. Then this becomes eta transpose lambda inverse eta. So that is what we will get here. Okay. So some of the comments that I should write as a follow-up of this one. So basically Bhattacharya bound is not one bound. It can be collection of several bounds, because you can take k equal to 2, k equal to 3, and so on. So depending upon how many derivatives you want to calculate, you can write different Bhattacharya bounds. Equality in Bhattacharya's bound . So if T is linearly related with S1, S2, Sk with probability 1, then equality will be attained. then it is sharper than the RCLB since multiple correlation coefficient between T and S1, S2, Sk is larger than correlation between T and S1. So this also means that because if you have more number of terms, then the multiple correlation coefficient increases. So if you increase K, then the Bhattacharya's bound gets sharper and sharper. But of course, it increases the difficulty of the problem also, because the higher order derivatives of this one will create a lot of complications. So it is not used in practice actually, but of course, we should be able to consider this at least. Okay, I will show you some example for calculation of Bhattacharya bound for a simple exercise. Okay. Let us take the example that we have already done. For RCLB, we have done this exercise. So I will take the same, that is the geometric distribution. Okay. Here RCLB, if you remember, what was RCLB? It was theta square into 1 minus theta. So if I take log of this, that was log of theta plus x log 1 minus theta. So we had this del fx theta by del theta divided by fx theta, that is derivative of this, that was equal to 1 by theta minus x by 1 minus theta. But for Bhattacharya bound, I have to consider more derivatives. So since I am taking only one term, so it will be like del 2f x theta by del theta 2. So if you consider further derivative, I will get the term as, I'm just writing down the straightforward calculations. It is a matter of writing down in a very careful way. So this will become 2 times. So if I divide, then okay. So let me write it the final form here after divisor. So if I consider the divisor here, that is f x theta, then I will get this term as minus 2x by theta into 1 minus theta plus x into x minus 1 by 1 minus theta square. What we will have to calculate? We have to calculate variance of S1, variance of S2, etc. So basically it means expectation of x square expectation, and here if I take square, I will get x cube as well as x to the power 4 also. So we need the moments of geometric distribution. So let me write it here, although you have done it in your probability course, but let me put this as an exercise also. Okay, please check all these calculations. So expectation of x square, that is 1 minus theta plus 1 minus theta square by theta square. Expectation of x cube, that is equal to 1 minus theta plus 4 times 1 minus theta square plus 1 minus theta cube divided by theta cube. And expectation of x to the power 4, that is 1 minus theta plus 11 1 minus theta square plus 11 1 minus theta cube plus 1 minus theta to the power 4. Please verify these things. I think you are already having in your probability course. So you just check whether it is written correctly. So we need here variance of S1, that is expectation of S1 square, that is 1 by theta square into 1 minus theta. This we have calculated for RCLB also. So just I am rewriting that. And expectation of S2 square, that is variance of S2, that is equal to 4 2 minus theta divided by theta to the power 4. Also you will need the covariance term here. That is covariance between S1 S2, that is expectation of S1 S2, that is equal to minus 2 by theta cube 1 minus theta. So the lambda matrix you will get as 1 by theta square into 1 minus theta minus 2 by theta cube 1 minus theta minus 2 by theta cube 1 minus theta and 4 into 2 minus theta divided by theta to the power 4 1 minus theta square. Since it is a 2 by 2 matrix, inverse is obvious. Because you will need the determinant of lambda, because I can interchange these terms and put minus there and divide by determinant. So that is 4 by theta to the power 6 into 1 minus theta cube. Of course, I will need these terms also. Eta 1, that is del g by del theta, that is 1. And eta 2, that is d2g by d theta 2, that is 0. Because derivative of theta is 1. So eta transpose vector, that is 1 0. And now I need to write lambda inverse matrix. So lambda inverse matrix is of course from this itself, that is 2 minus theta, theta square into 1 minus theta, theta cube 1 minus theta square by 2 and 1 by 4 theta to the power 4 1 minus theta square. So the Bhattacharya's bound eta transpose lambda inverse eta, that is equal to theta square 1 minus theta into 2 minus theta. Actually, it is greater than theta square into 1 minus theta, that is the RCLB. So you can see that this is sharper. So this is just an example of the calculations here. And you can see that just for the second order application of this Bhattacharya's lower bound, we need to do a lot of evaluations here. So are these calculations clear to you? Of course, you will need these moments of the geometric distribution which you have done in your probability course. So just you have to revise again those things. If you don't have those expressions, just calculate it again. I have put it as an exercise for you. So is that okay? Do you follow these calculations?
Yes, sir.
Now, what is the meaning of taking derivative actually? Derivative is basically writing down a difference and then dividing by the length of the interval and taking the limit. Okay. And in order to do that, we are able to obtain this lower bounds. But at the same time, we are putting some conditions on the distributions, isn't it? That integral under the differentiation sign is allowed and so on. But when we were finding out the maximum likelihood estimators, you have seen that in some distributions, the method of maximum likelihood was not directly like you differentiate and put equal to 0, etc. But you applied some direct argument, like in the uniform distribution, like in the exponential distribution with parameter mu, etc. There, this differentiation under the integral sign is not permissible because you cannot separate out the range of variable and the parameter. So in such cases, another inequality has been developed where the regularity conditions are not used. Okay. Of course, you can understand that this will be weak. So another inequality has been developed where the regularity conditions are not required. Okay. So one of them is actually more popular one. We call it CRK inequality. That is named after Chapman, Robbins, D.G. Chapman, Herbert Robbins, and Jack Kiefer. So this is 1951. They, of course, all of them obtained independently. So we name after all of them CRK inequality. So again, let us consider, say, X have a PDF or PMF fx theta and let T be an unbiased estimator of, say, g theta. We also define another quantity called a phi theta to be variance of fx phi divided by fx theta. That means I write the density function or the mass function by changing parameter theta to phi and then write this ratio and look at the variance of this. Okay. Of course, this should be well defined because if the density is 0, then this is not defined. So I am defining it over the range, that is fx phi is positive. This should be subset of the range of where fx theta is positive, because this should not become infinite. This should be well defined. So the CRK inequality states that variance of T is always greater than or equal to supremum of phi of g phi minus g theta whole square divided by a phi theta. Okay, so is the statement clear to all of you? Of course, this is not a very difficult statement. Are these definitions clear to you? What I have written here, a phi theta and then this inequality. Is it okay to you? Is the statement clear to you?
Yes, sir.
So let us look at the proof of this. G phi minus g theta, that is expectation of Tx when parameter is phi minus expectation of Tx when the parameter is theta. So this is nothing but the integral of Tx fx phi dx minus integral Tx fx theta dx. So these terms we combine together. We can write it as Tx fx phi minus fx theta divided by fx theta into fx theta. Of course, I am assuming here continuous distribution. If discrete is there, then these things will be replaced by summation signs. So this is nothing but expectation of Tx and this term is nothing but fx phi by fx theta minus 1. Once again, you can see actually expectation of this fx phi by fx theta, that is actually equal to integral fx phi by fx theta. So here I'll put distribution as theta, fx theta dx. So that cancels out, so this is equal to 1. So expectation of this term is actually 0. Okay. So this I can consider again as covariance between Tx and fx phi by fx theta minus 1. And this constant will not matter because when you take covariance with a constant, then that is again 0. So it is nothing but this term itself. So we have g phi minus g theta whole square is equal to covariance square Tx fx phi by fx theta. So by applying the covariance inequality, I will get this is less than or equal to variance of t into variance of fx phi by fx theta. Which implies that variance of t is greater than or equal to g phi minus g theta square divided by a phi theta. Now, if you look at the left hand side, there is no phi coming here. So I can take supremum on the right side. Okay. So this implies variance of t is greater than or equal to supremum over phi g phi minus g theta whole square divided by a phi theta. So actually in the limit, this is same as RCLB. If I take the limit of phi tending to theta, then I will get actually RCLB. So this is actually, you can consider a discretized version of that inequality. But then here I don't need any conditions on the density about differentiability under the integral sign. None of those conditions are required here. So I will give you applications of this to the non-regular distributions, how to calculate this one in the next class. In the meantime, I have given you several exercises with red color. You please solve those problems, okay? That is very important to learn the calculations when you are doing inference. I think I have not taken a break now, so I think we can stop today's class. It's almost time, okay?